than your own sense of smell. There are ways to do these kinds of experiments with dogs. Okay, from Weber's law, we then get Fechner's law, okay? Again, following on Weber's work, basically a translation into a more general principle, S equals K log I, and that simply means that for every physical property of a stimulus, there's some logarithmic function that relates the physical stimulus to the sensory experience. And this is just a plotting. This is just a plotting of the data I showed you before on a different scale, and you get this nice negatively accelerated function, so that the log here, okay, there's just 1, okay, for 10, you get 1. For 100, okay, you're up to 2. For 200, you're up to 2.3, and so on. That's just exactly what Weber's fraction would give you. Plot these things, yeah, there we go. Plot these things on logarithmic paper, you get a straight line. You finally do get an isomorphism, right, between physical stimulation and sensory experience. You got to use logarithmic paper to do it. These guys loved straight lines, okay? And the reason I love straight lines is there's something that seems really natural about a straight line. When you get a straight line connecting all your points, you think you've really found something important. And so Fechner's law got established pretty fast. What does this mean in English? Okay, what it means in English really is that, as a rule, sensation grows more slowly than stimulation. Okay, small changes in stimulation give rise to even smaller changes in sensation. Even big changes in stimulation give rise to relatively small changes in sensation. And that is a general psychophysical law. Fechner's law holds across a wide range of modalities and stimuli and all of that. There are some exceptions, however. That's not the case for perceived length. Perceived length grows exactly with physical length, and that's not true for perceived pain. Next time you're at the dentist and he's drilling, ask him to press down just a little bit more, okay? And what you'll find is that the pain mounts very quickly, right, under those circumstances. So there are some exceptions to Fechner's law, which gave rise to what's known as Stevens' law, the last of these laws from S.S. Stevens. For those of you who are skiers, Smitty Stevens introduced the short ski to North America. It's probably more famous for that than for anything else outside of psychology. But again, what Stevens' law basically says is reformulation here, S equals Ki to the n. And what Stevens' law says is for every quality of sensation, there is some exponent, n, that relates the physical feature to the psychological feature of a sensory experience. In the usual case, that exponent n is less than 1. It's a fraction, and that gives rise to Fechner's law. Okay, but in other cases, the exponent may be exactly 1. Where are we here? Okay, in the case of length, the exponent is exactly 1, so that there's a 1-to-1 correspondence between perceived length and physical length. And in the case of pain, the exponent is greater than 1, which is the case where sensation actually grows more rapidly than stimulation. Those details are not as important as the law itself and the enterprise of trying to establish mathematical relationships between the physics of a stimulus and the psychology of sensation. Again, this is an early scientific approach to consciousness that has had quite a bit of influence both on the study of consciousness and, for that matter, the rest of sensation and perception. Okay? So the reason I go over this is that psychophysics, especially 19th century psychophysics, of which Stevens' law is really the apex, okay, the the zenith of all of this, is an example of an early scientific approach to consciousness, trying to relate the psychological qualities of conscious experience to the physical qualities of the stimuli that give rise to those experiences. So we have all, in psychophysics, we have pretty much all the qualities that you'd want in science. You have first empirical studies. We're not talking about William James's introspections or Descartes' introspections or Kant's introspections anymore. We're talking about empirical studies that that involve systematic observation of typically more than one subject, a representative sample of the population at large. And instead of just kind of sitting down in your armchair one day and looking at the contents of your own mind, you've got experimentation that occurs under very, very, very rigorously controlled circumstances. Moreover, you've got quantitative data. You've got people assigning numbers to the brightness of a light, the loudness of a tone, the strength of a taste, or whatever. And you've got statistical analyses that allow you to relate those numbers that are generated by the observers to numbers that are generated by physical various kinds of measurements. And then finally, you get these nice mathematical functions that relate the properties of some stimulus environment, like how the luminance of a light or the decibels of a sound or whatever, to a person's conscious sensory experience. Psychophysics, therefore, really counts as the first scientific approach to consciousness, the first way in which psychologists, physiologists, even philosophers, some of them, tried to relate conscious experience to something that is objectively, publicly measurable and confirmable. Okay, anything about psychophysics at the moment? There's a lot more on this in the lecture supplements for those of you who are interested. Okay, let's look at another trend that was a scientific approach to consciousness and go beyond intensity. Okay, intensity is a feature or a property that is characteristic of all sensory modalities. In vision, lights are brighter or dimmer. In sound, in audition, sounds are louder or softer or whatever. That's the same thing for taste and so on. You can be more or less off balance. You can be more or less in motion and all of that. But what's interesting about sensation is that although intensity is a quality that all sensory modalities have in common, there are also specific qualities within a modality. In vision, we have, for example, hue, roughly color, and saturation, roughly how intense the color is. In audition, in addition to intensity, we have pitch, whether a sound is high or whether it's low, and you have timbre, like the difference between the sound of a clarinet and the sound of an oboe. The psychophysical law applies here as well. The general idea is that each of these sensory qualities is also related to some physical quality of the stimulus. So, for example, hue is roughly related to the wavelength of light, and pitch is roughly related to the frequency of a sound. Saturation is related to the amount of white that's mixed in with the light. Timbre is related to the exact shape of the auditory wave. Again, we don't have to go into those details, but the idea is that the psychophysical law applies to these qualities of sensation as well, and all of this has been worked out best and most satisfactorily with the color. So, for example, here you've got green. That's supposed to be a pure green. Okay, roughly the 495 nanometers in wavelength. Pure blue, 465. The pure yellow, 570. So that's hue. And then saturation, actually, I misspoke before. It's not the amount of white, of course. It's the amount of gray that's mixed in. Here's pure red, 700 nanometers of wavelength. You mix in some gray, and you get this kind of washed out pinkish kind of red. So again, here's an example of how quality, hue, or saturation is related to a physical quality of the stimulus. You can see the same thing with auditory sensation. Here's the musical staff here. Middle C, about 262 cycles per second. The second space C on the bass clef, about 131 cycles per second. Third space C in the treble clef, about 523 cycles per second. Each of the octaves is a multiple of each other. 262, so 131 times 2. And then timbre, you can see it's the shape of the wave. Here's a violin, kind of a nice sine wave, pretty much. Here's a trumpet, much sharper transitions. The flute, again, nice, pretty sinusoidal a wave. An oboe, much more of a sawtooth kind of wave. And basically, timbre is given by how many harmonics there are laid on top of a fundamental pitch. Again, we don't have to go into that, except that it makes the point that each psychological quality of sensation is related to a physical quality of the stimulus. And Miller's student Helmholtz thought that each of these qualities, too, was mediated by a specific nerve fiber that functioned according to a specific kind of energy. And again, he was wrong about that, but it turns out that it was right to argue that there are specialized neural structures that handle things like saturation and color and all of that. We know about rods and cones and opponent processes and all of that for color vision. So again, you've got this psychophysical principle leading to this idea that there are different physiological structures, different neural structures that are processing each of these various kinds of qualities. So where do we get this? Well, a lot of this we get from a kind of psychology known as structuralism, which engaged in this very systematically controlled introspection to try to identify what the fundamental qualities are of various kinds of sensory experiences. So Wundt and Titchener and other guys like that would have people come into the laboratory, they'd set before them some kind of stimulus, and then they'd ask them simply to introspect on what they see, okay, and to try to analyze what they see or what they hear into its component parts of sensations and images and feelings and so on. This is a kind of a mental chemistry, if you will, where the overall experience is conceived as a kind of molecule, and the goal of structuralism, the goal of structuralist introspection, is to analyze that molecule into its constituent atoms, its atomic elements that can not be further analyzed into something smaller. Here is an example of that. Forget the stimulus error. Here's the color circle, lots of different colors. And it turns out that when you look at any portion of the color circle and you're asked to analyze what you basically see is some combination of 4 primary colors: red, yellow, green, and blue. Any color that you see in paint chips in the paint store or clothing in a clothing store can be analyzed into some mix of red, green,